Paul Cobb is a research professor of mathematics education and Peabody Chair Emeritus at Vanderbilt University. And you've probably had a chance to read these other things that he won an award from the International Commission on Mathematics Instruction and the American Educational Research Association. He's written some very interesting books. His life works were published by Springer 10 years ago, and he's been working with districts, urban districts for some time, and has published a book that I've had checked out from the OU library for 3 years. And his work is on large-scale instructional improvement. Lately, he and his colleagues have collaborated with large urban school districts to provide detailed, actionable feedback to improve mathematics instruction. His bachelor's degree is from the University of Bristol. So as you may have already noticed, his accent is not typical of Nashville, Tennessee. He comes from the southeast of England. His master's and PhD are from the University of Georgia in Athens. And so I'm going to stop sharing and turn it over to you, Paul. Thank you so much for being here today.
Thank you. I really appreciate the invitation. And as I told Greg earlier, you're about to see the world's messiest desktop as I try and share. So let's see. And I'm assuming that's sharing now. So
yes, it's great.
Put that away. And let me go to full screen. Whoops. I want to go to slideshow. I'll figure out how to do it.
There you go.
Got it. Great. So Greg already said a number of things I thought I'd have to say about my background. So I just want to reiterate that the issue I've been really interested in for the last 15 years is that of what it takes to improve the quality of math teaching and students' learning at a large scale, meaning across a large urban district. And so for 10 years, from about 2006 to 16, I and a lot of colleagues, a group of us, collaborated with 4 urban districts that served a total of 360,000 students. And these were genuine partnerships where we did research with rather than on the districts. And we were trying to figure out what it takes to support instructional improvement at scale. For the last, I'm in the 5th year now of partnering, and again, it's a genuine partnership with my local district, Metro Nashville Public Schools, which has been a joy for many reasons, one of which I don't spend half my life on planes. And so that's just the backdrop against which I'm approaching this issue. This is Nashville's, what they would say is the theory of action for instructional improvement in mathematics. But it also, as it turns out, is a pretty good overview of this talk. One way to look at it, where you can see from the direction of the arrows they have, their primary support for teachers to improve, math teachers to improve, is one-on-one coaching. And the idea is if they can support coaches in becoming proficient, that will lead to improvements in the quality of teaching, which will lead to improved student learning. I think there's nothing sort of dramatic or radical or unusual about this. And this, I think, is exactly how the folks on the panel thought about this issue just now. I'm going to follow in their footsteps by starting out by focusing on students' learning to start with, very briefly. Why? Because I take the view, and I think the panel members did as well, teaching is at the service of student learning. Improving teaching is not an end in itself. The end is improved student learning. If we understand what learning goals for students are aiming for, that has implications for what counts as good math teaching. And that then has implications for what, in the case of the district I work with, partner with, what counts as high quality one-on-one coaching. So that's the basic plan I have. And as a first step, and I've asked Greg and also Nancy to help me out if I'm addressing issues that are either you already discussed in previous meetings or I need to say more. But what I was going to do to start with is just have you compare two assessment items. We're all aware that there's been an increase in the rigor of state assessments, state standards. This is from one of the districts, one of the states in which we worked in that first period between 6 and 2016. This is the prior assessment. This is a 7th grade item on the state assessment to assess kids, I guess, concepts, understanding, and volume. You can see it's a very simple item. So you might just want to remember it's a box. You can take down the dimensions, though. I certainly don't expect you or want you necessarily to actually solve the problem. And here's the second item. This is from the subsequent assessment after the standards increased in rigor. On volume, look at the difference from a very simple box problem. Here it is, a pool's being filled up. Here's the volume of the pool. Here's how many gallons per minute. At this rate, how many minutes will it take to fill this pool 3/4 full? That's the problem. There was a different version for special education students. The only change was how many minutes will it take to fill this pool half full? Now, I'm going to put this problem back up in a minute, but here's the questions I'm going to ask you to do for just 3 or 4 minutes in breakout, and then type your answers in the chat. What do you, or what would a student have to know to solve the first task, the box problem? What would a student have to know to solve the second task, the pool problem? But the question I really want to ask, and I couldn't figure out how to word it, is what capabilities do students have to develop to solve the pool task that they didn't need to solve the box task, if that makes sense?
So if you're back, if you can type into chat questions that came up in your breakout rooms, that questions you wish to ask Paul, or comments you wish to make, or responses to the questions that he asked. And we have from Chrissy Pratt, for the box task, you only need to know formula for volume and how to compute. Please type in chat thoughts that came up in your breakout room. In one breakout room, I heard people talking about how realistic were these problems. And if you were filling your pool, how would you know it was a rate of 40 gallons per minute? I wish when I filled my hot tub up, I would know some things like that. How fast is the hose filling the hot tub? So, can I come back in 20 minutes, or do I need to check? And the realism of the problems, what I did come up. And then we've got, what is the diameter of the hose? Second, two problems. The second problem has 2 parts to it. The pool problem, you already need to know how to compute. And Mikesell has a great way of thinking about the box, and the strategy chosen by the student would determine what a student has to know. And can you share your thoughts just real quickly with us?
Sure, I was typing them in the chat. On the box problem, I thought about how I would solve that problem today, as opposed to how I would solve it when I was in school. And I would just use my understanding of volume of filling the box with cubes. It was kind of convenient that the dimensions were 1 inch. So if I use 1 inch cubes and line them up inside the box, I can find the volume. I need to recognize that since the depth is only 1/2 inch, then the volume would be equal to half of the number of cubes.
Okay.
Paul, I didn't need the formula.
Right, I understand. Go ahead, Paul.
All I was saying, now was that last person, I'm sorry, I didn't catch your name. Was it Anne?
Yeah.
Yes.
Yeah. I understand what Anne's saying, how you do it, but that's because you've already got a sophisticated understanding of volume. I was thinking if you're a kid, and the question I always ask when I look at these problems is, what's the least you have to know to be able to do this? Because when I look at a classroom, I always say to myself, what do kids have to know to be effective in this classroom, to be viewed as successful? And what's the least they have to know, rather than over-attributing to them? And what I want to suggest is, on this problem, the box problem, the least they have to know, I think Chrissy maybe put it in, one of the first people who typed in a response, is you can get away, if this is a familiar problem to you, with just knowing the formula, and you just multiply the three numbers. And I want to suggest that for many kids, and I agree with many of the comments said, this is one of those typical problems that really was on a state assessment, the lack of reality of it, but this is the problem. Typically, this is not going to be a familiar type of problem to kids. And so they have to analyze, and I think somebody used the word relational understanding, old Skemp's term, have to actually understand what's happening in that situation and understand the relationships between the quantities involved. You've got time passing, and you've got water going in, you've got the water level going out, that sort of thing, in order to figure out what they need to compute, which procedures to use. And I don't know if that seems reasonable or not. The reason why I wanted to raise this question, and I'll try and go back to full screen, the reason why I wanted to raise this issue is because we found in our work, we work not just with teachers, not just with coaches, but we've also involved school leaders and district leaders. In other words, we're interested in the whole system. And we found that school leaders and district leaders and people who aren't math specialists, when we talk about more rigorous standards, they tend to think it just means harder sums. Maybe instead of adding 2 numbers, you have to add 3 numbers, or the numbers are bigger, rather than the new standards imply that kids have to develop a whole new set of mathematical capabilities. And the way this is the top end of a little rubric we developed in collaboration with the math coaches in Nashville, a tool that they could use. And we got it down to just 3 levels, or 3 levels of rigor. Low-level tasks would just be using known procedures, very familiar procedures. The box task. At the top end, what we call problem solving, and the task there is very similar. It's just an analog of the pool problem you saw. The big thing is, the new capability is students have to analyze the problem in order to figure out which procedures to use. That whole capability of actually analyzing novel situations in terms of the relationships between quantities and so forth, that's an entirely new capability they didn't have to develop in order to be successful previously. And in the middle, we've got a level called where students, yes, they use procedures, but they have to figure out why the procedures work. And we've got an example of a task there. And on our little rubric, we have examples from volume, we have examples from data, and we also have examples from linear algebra, just as a way of going about it. And for us, this was important to make these distinctions and to realize that if we want to have instruction improvement scale, we have to take account not just of teachers, of coaches, of math specialists, but also of school leaders. And so part of what we were trying to do was figure out what they need to do. The big point is that goals for students' learning have changed. We also have to support kids in analyzing problems. If we're going to do that, we have to have analyzable problems. And in the panel, one gentleman spoke of using rich tasks and so on. Exactly. A lot of work the motivation or the rationale for ambitious and equitable math teaching is precisely to enable or support kids in developing those new capabilities. that weren't essential before the standards increased in rigor. And the basic template of ambitious and equitable instruction, as I'm sure many of you know, is to introduce or launch rigorous math tasks, ideally so all kids can begin to work productively on the tasks, then work either individually or in small groups, and then a whole class discussion. And over the years, there's been an enormous amount of research on what specifically a high quality whole class discussion looks like, and looking at how teachers can support kids in explaining and justifying reasoning, how they can support kids in making connections between different solutions. One other thing I might mention with regard to the tasks, and this was sparked by a gentleman who was talking in the panel and talked about, I think, his wife and had these classes with kids at different levels. One of the important characteristics is not just the level of challenge of tasks, but also they have, quote, multiple entry points, meaning they can be approached by kids at different levels. And while some kids might develop much more sophisticated solutions than others, all can actually engage meaningfully with the task, would be another important characteristic here. But something beyond that basic template we've come to see as really important in our work with districts is getting very specific about what teachers need to know and be able to do in each of these aspects. And I want to give an illustration by focusing on the launch, introducing or launching tasks. Why is this important? I mentioned we worked with those districts for 10 years from 2006 to 16. In that work, we ended up videotaping 1,700 math lessons for in these urban districts for middle grades. We coded all of those lessons. One thing that came out when we looked at the launches, how they were introduced, in 2/3 of them, if teachers used rigorous tasks, more challenging tasks, they proceduralized the tasks when they introduced them. They basically converted them into regular procedural tasks, taking away the challenge from the kids. We saw that as a real issue for equity. And we did find some teachers who were very handy at introducing tasks. Not many, but we found them. So we analyzed those cases to figure out what is it those teachers were actually doing to enable, not showing the kids how to solve the task, not reducing the challenge, but what work were they doing to enable all of their kids to begin working on the task? And we found 3 things, 2 of which I think will not surprise you. One, they clarified the contextual features of the task. So if we go back to the pool problem, they would spend time having kids talk about, have you ever been to a swimming pool? You know, it's got lots of water in it, how they change all of that sort of business. So they actually have in imagery in their minds an understanding of the situation of the task context. They also, especially in so many classes where we worked, a significant number of kids whose first language is English, spent time with the kids to clarify issues of language in task statements. That's typically what gets talked about, especially if we're interested in equity, and it's really important. But also what these teachers were doing was understanding key mathematical ideas needed to understand what the task is asking. Notice here, not to be able to solve it, but to understand what the problem's asking them. So in the case of that pool problem, again, it's that relationship between time passing and the water level going up, the filling, the increase, increasing the amount of water in the pool. That's the critical relation. And they would work to help kids understand that relation so that they could begin to work on it as a key aspect. That's a different capability than typically gets talked about and perhaps addressed in our pre-service programs, but one we see particularly critical, and again, without suggesting a particular solution method. And that, I think, is a way to get at issues of relation. Now, one thing we did, I showed you that little rubric, and I will just mention this in passing and come back to it later. We've been developing in the more recent work what we call practical measures. And here's a practical measure for the launch. very short survey, a student survey, not a teacher survey. It's just got 4 items on it. And it can be given, the reason why we want these short, kids have got to be able to complete them in 90 seconds or less. So it doesn't take away from the instruction. It doesn't disrupt the teaching. Can you picture what's happening in the problem? In other words, do you understand the context? Do you understand what you're supposed to figure out? Are you ready to get started and list any words in the problems that you don't understand? A very simple little survey that gives teachers feedback on their launches with a view to helping them improve or get back better at launching tasks. And we've actually developed 4 practical measures: the rigor of the task, the rubric I showed you, 1 for the launch, 1 for small group work, and 1 for whole class discussions. Again, those last 3 are all student surveys, which gives kids some voice if they're taken seriously. And we see 2 initial benefits for these things. When we developed each of these surveys, as in the case of the launch, we looked at where is there evidence that this aspect of the launch or of the whole class discussion, actually there's evidence it actually matters for kids learning. We're not, so it would be things in the whole class discussion like, did you have trouble understanding other students' explanations or not? So pretty basic stuff, but things that really matter for kids learning. We worked very hard to get items that would communicate to students and to which they could respond. It can orient practitioners to focus on the aspects of practice that actually matter for student learning. So if you look at your students' responses and it comes back and they say, I couldn't picture what, a lot of them say, I couldn't picture what was happening in the problem. That will hopefully orient teachers to focus on what did I do to introduce? How could I have done that better? And to begin to improve the aspects of instruction that really matter. And it also enables practitioners to determine whether a change is in fact an improvement. So you get it back, they're struggling on the issue. They say, we can't picture what's happening in the past. So you make some changes and you try some different things for the next task. Then you give the survey again. It only takes you a minute. And then you can look, is it better? Is it an improvement or not? So our friends at the Carnegie Foundation have a slogan, you can't improve what you can't see. And I think that's right. And what they mean is, if we do things and we don't know what its effects are, we can't improve it. We have to be able to get that feedback. So these are very simple measures. You can see they're absolutely not used for accountability. They might be called improvement measures instead of practical measures. That might be a better word, but they're specifically designed to help teachers and the folks who work improve their instruction. So thus far, in this little tiny piece of the talk, I've just focused on the doing of teaching. But there's also been a lot of work on what teachers need to know and know in order to do these things. And I think would most people here be familiar with mathematical knowledge for teaching?
I would say at least half.
So maybe I should just say a few. Yeah.
Say briefly, I think, to help.
So I'm thinking back to when I started graduate school, as a few of the astute members of the audience might have noticed, this wasn't yesterday. And I remember I took a very first class, my first semester. We read a book by a guy called Ed Beagle, and he was trying to synthesize what was known about math research at that time. And there was a big conundrum. So this was in the late 70s. A big issue was this. Everybody had this really strong intuition that it was really important for teachers to have a deep understanding, deep knowledge of math if they're going to be good math teachers. Yet nobody could show this was the case. They would go out, they would look at math teachers, how well they taught or how well their kids did, and what courses they took in college, whether they had a master's degree, they gave them math tests. None of it seemed to make any difference. No relation between any of that and student teaching. That continued way after that Beagle book. And it was only, I would say, about 15 years ago when Deborah Ball and her colleagues at Michigan made the breakthrough. I know Deborah pretty well, and she at that time was teaching a second grade class every day in the university school. And she would view her own math background as pretty weak. And so one of the things she was focusing on in her practice as a teacher is, where do I actually use math? What are the mathematical problems that come up for me as I'm either teaching, as I'm preparing to teach, or as I'm reflecting and analyzing my teaching, or I'm looking at my students' work, or whatever else it is. And that led her to develop, and her colleagues to develop, this notion of mathematical knowledge for teaching. It's mathematical knowledge that's specific to teaching. It's different than mathematical knowledge for being an engineer, for being an architect, and for other professions. And so the sort of problems that they would have, and they've got it down to now to a multiple choice instrument, would be, here's a non-standard solution the students use for a particular problem. The teacher wants to know, is this a legitimate solution? You got the right answer to this task. Was that lucky, or will it always work? So it'd be problems like that that try to get at the sorts of issues that teachers really have to address in their practice. It turns out this makes a difference, and it's equivalent to about an additional 3 weeks of instruction a year if a teacher has pretty sophisticated mathematical knowledge for teaching. Very important. I think this is great work, but the problem from my point of view is we have an instrument for this, and it's now all we think teachers need to know. Don't want to downplay mathematical knowledge for teaching at all, quite the reverse, but I also want to suggest two other aspects of teachers' knowledge and perspectives. The first is, what is teachers' visions of high quality math instruction? And we assessed this in our big study, actually, the earlier one. We interviewed these folks every year. This was teachers all the way up through school leaders and district leaders, so 1,600 audio recorded interviews. And we asked them each time, suppose you can go into a math class and you can stay there as long as you like. What would you look for to know if it's good teaching, high quality teaching? And that open response, we had follow-ups. We pressed people on, if it's good teaching, what would the tasks look like? And if they use words like problem solving, because they could you actually give me an example of a task? We asked them, would there be a whole class discussion? Yeah, who would be doing the talking? What would they be talking about? And then we'd say, what's the role of the teacher in those discussions? And if they said facilitator, what would the facilitator, pressing them for the specifics to get beyond these sort of buzzwords? And we formally coded these things up. The fellow who developed this was Charles Munter, who was at that time a doctoral student. And he and his colleague, Rip Correnti, showed, because again, a lot of data, so we can do quantitative analyses, that developing a sophisticated vision of high quality math instruction consistent with ambitious and equitable instruction is a precursor, it's a leading indicator of improvements in teaching. And we think that makes sense. It's very hard to develop a form of teaching, a particular teaching practice, if you haven't got a clue what it looks like. So it's not the same. You're not there if you've developed a high quality vision, but if you haven't already developed a high quality vision, it's impossible to develop those forms of practice. The second one, which I also think is critical from the point of view of equity, we call view of students' current mathematical capabilities. And again, we ask this to people all the way up and down the line, but just focusing on teachers. In the interview, again, we'd say, have you got any kids who are currently struggling? And they would chuckle, almost always chuckle and say, yeah, I have. And we say, well, who are these kids? And we're trying to figure out from their point of view, is it the poor kids? Is it kids whose first language isn't English? Is it the African-American boys? Who is it? But then the key thing we ask is, why do you think these kids are struggling? And we code those responses on a scale that goes, at one end, we call it unproductive. And unproductive would mean they attribute the cause of the kid's difficulty to something inherent in the kid. They don't care, they're lazy, or to the family or the the community. The parents don't care. They're working 3 jobs. They're too busy. And the reason why we code this as unproductive, it attributes the source to something beyond their control, something beyond the school's control. There's nothing we can do about it. For productive responses, would attribute the source of the kids' current struggles to their limited opportunities, either now or in the past. It might be, how that they might actually look at their own teaching, or they might look at what happened in previous grade levels or whatever, and we code those as productive. And then we follow up by asking them, for those kids who are struggling, what do you do to support them? And unproductive responses would talk about lowering the level of rigor. It would talk about proceduralizing tasks, and a lot of them, we also found a lot of them actually simply skip the more challenging parts of tasks. So in other words, they're sort of giving these kids who they perceive to be struggling, many of whom are brown, Black, first language isn't English, a much lower level education than other kids. Or those would be the main reasons. For teachers who we would productive responses, they would provide extra supports for those students. They might pre-teach some of the concepts kids need to understand in order to understand what tasks are asking, for example. And we call this, again, views of students' current mathematical capabilities. What we found was quite depressing. We had 120 teachers each year in that study for 8 years. So we actually started collecting data in 2007, so it went for 8 years. Less than 20% of the teachers attributed kids' struggles to limited instructional schooling opportunities, okay? Almost 30% attributed the kids' struggles solely to deficits in kids or their families. And less than 20% describe making productive adjustments. I'll be honest with you, that was not a surprising finding. I'm just trying to wave our hands like, this matters, we've got a real problem here. And I'll explain why in a minute. Does having a more advanced or more productive VSMC matter? Well, yes, it does, because remember we had all those videos of the same teachers at the same time? So we can look at the relationship between their VSMC and the aspects of their instruction. And if we do some fancy statistical footwork and factor out the depth of their mathematical knowledge for teaching, we factor out the sophistication of their instruction vision, VSMC still makes a difference. In other words, teachers who have a more productive VSMC are more likely to maintain the cognitive demand of tasks. They're not going to proceduralize. If you think your kids really aren't up to it, that's a primary reason to proceduralize, okay? And I will mention this in passing. We also, 3 of these 4 districts had adopted inquiry-oriented math curriculum, a pretty good one. This was middle grades, connected math. Quite a lot of pushback and resistance. Looking through the data, the primary, not the only, but the biggest reason for that pushback was teachers thought their kids weren't up to it, unproductive VSMC. So this matters in lots of ways. If teachers who thought their kids were up to the challenge tended to maintain the level of cognitive demand of tasks, they also conducted higher quality whole class discussions in which kids were actually expected to explain and justify their reasoning. And last but not least is this. This is a dissertation by one of my students, Charlotte Dunlap. And she said, why is it, if you look across years, because remember we got data across multiple years on these teachers, why is it some teachers get better over time? Some teachers really don't change at all. And some, heaven help us, actually, the quality of their instruction declines. Clearly, that relates to having access to high quality supports for their learning. But it wasn't just that. She also looked at some of the, quote, teacher characteristics. And she found that teachers' instruction was unlikely to improve unless they have developed both relatively sophisticated views of high quality math instruction and they have productive views of students' math capabilities. that makes sense if we think about it. Again, if you have to have that sophisticated image to know what it looks like. But we found some teachers who did have a pretty sophisticated image, and they still were not improving. And we found those teachers typically would say, well, yeah, that's good for other people's kids, but my kids aren't up to it. They can't do it. So therefore, and so even if you provided high quality professional development, even if there was a pretty handy coach available in the school, those folks did not want to avail themselves of those opportunities because they just saw it as a waste of time for their students. So again, this matters. So what I'd like to do is to have another little breakout. And what I want to ask you is, what do you see as the implications of these findings, particularly about teachers' views of their students' math capability for your work or the type of work you used to do? Whether it's you're supporting teachers, working with teachers, whether you might be teaching pre-service education classes. And this is math, but I have to assume there is something similar going on in science, for example. A lot of teachers would say, my kids aren't up to it. This sort of more conceptual, investigative sort of science. So maybe we can take just 5 minutes to go back to breakout groups. And again, we'll come back after 4 or 5 minutes, and then we'll look at people's responses. So maybe I'm interested to hear the sort of a couple of responses groups had to this question of what do they see as the implications. Maybe there's none implications for their work, whatever that may be. Okay.
If you are back, go ahead and put in what are the implications for your work. We've got Gabrielle Motney from Bowling Green State University is saying, haha, yeah. I noted that you likely hit the wrong button. No, he's responding to Kim Yoke's question. Marzano noted that we need to model learning techniques that we want students to use. And that's a comment from Janet Hirelko. Yeah. And then Jerry's talking about constant comments, school teachers' attitudes change when they work together with students, and those of profs who are teaching pre-service teachers, school teachers' attitudes, and those a professional development coordinator is important to realize that content is important. What we talked about was the importance of professional development and how this needs to include ongoing support. So I don't know, are you seeing the chat, Paul?
Yep, I got it right here.
Okay.
Yeah. I think there's a lot of good ideas here. Now I just think, as I'm going to start, I'm currently in Nashville. Their priority is one-on-one coaching. And so what we've been doing for the last 4 years, we being the maths specialists and the lead coaches, is co-designing and co-leading and then co-analyzing professional development, not for teachers, but for coaches. The reason why I want to work at that level, but don't do teacher PD, is because we see the problem as that of supporting the development of districts' capacity to support teachers in getting better, if you know what I mean. So our little stake in the ground is around coaching, because that's the district's priority. In the context of that work, what this tells us is, but heck, our work's going to be unsuccessful unless we can support the coaches to support the teachers in developing more productive views of their kids' mathematical capabilities pretty early. If the teachers have unproductive views, they're going to resist, or maybe just you'll get sort of symbolic compliance with the coaches, but they won't actually change anything they do in their instruction. So this, I guess I'm trying to illustrate it, has very direct implications. I think if you're in any way involved in trying to support teachers in improving how they work with kids. The other thing we've come to think of it, there's a sort of vicious cycle going on here. Teachers would say, my kids aren't capable of this. Why did they say that? In a way, they're not wrong. If you go into those teachers' kids' classrooms and the kids really aren't motivated, they really don't care. The issue is they're seeing those kids in the context of how they currently teach, where they're proceduralizing tasks, where it really is astonishingly boring and whatever. So part of what we work on with our coaches is them, co-planning, then modeling instruction, where the charge for the teacher is not to come in and teach, just sit with a group of kids, hopefully one of the groups they consider to be a very weak group of students, and focus on what those kids are doing mathematically, and then debrief, not initially about the instruction, but about what those kids could do. Were you surprised or not, and so on. And then why was it those kids were able to do that today? The thing about this notion of views of students' math capabilities is not a prediction. You remember the old expectations research? Where will these kids be at the end of the year? It's not that. It's a prediction about what they can do in the next hour if they are supported appropriately. And that's the astonishing thing about this, that teachers have worked with these kids day in and day out for, say, half of a school year, and yet their predictions on that are inappropriate if these kids are supported. So that's the point we're trying to make. We see this as potentially a solvable problem. It can be addressed, but it needs pretty skilled people to work with teachers to support them in developing those more productive views. And I want to do I just conferred with Greg, and we're just going to take the last 5 or 10 minutes here just to touch briefly on the coaching work. And the goal for the coaches we work with is to have high quality enactments or implementation of one-on-one coaching cycles. And many of you might be familiar with coaching cycles, not original to us at all. Initially, the coach and teacher co-plan a lesson together. They select learning goals for students, they select tasks, they plan how they're going to implement the task, how they're going to launch the task, and so on. Then there's a classroom phase in which, and typically in a coaching cycle, the coach observes, the teacher teaches it. We would broaden that so coaches make a principled decision about whether to model. And I just showed you an example of when it makes sense to model or to co-teach or to observe, and then they debrief. And we talked about, even if you model and you're focusing on VSMC, you still want to debrief afterwards. Very important. There is evidence that coaching cycles can really have an impact in supporting teachers' learning, hence why we focus on it. One thing, though, that we found, we didn't plan to do this, but we had to actually make some changes or some elaborations. And I'll tell you a story of what happened. The first year, we co-planned the PD, and we met very regularly before and after every session with our district colleagues, but we were responsible for leading the PD, primarily a doctoral student, though I aided and abetted, a guy called Nick Komenczki. And about the third or fourth session, the wheels really came off. We had a case, an instructional case. It was based on a real class we'd observed, where the teacher had a challenging task, launched it very confusingly. The kids then worked on it, and we just gave a summary of the kids' work. And basically, they were trying to figure out, they had no idea what the task was asking. They were trying to figure out what they should, just doing things with numbers. Then the teacher tried to lead a whole class discussion, which was a bit of a mess. So we described this. We asked the teachers, the coaches, 15 of them, what would be your goal for this teacher's learning? What would be your instruction improvement goal for this teacher? And they all said, without hesitation, questioning in whole class discussions. From our point of view, this would be an unproductive goal, improvement goal. Why? Even if you improve the questioning, that's not where the lesson broke. The learning broke down. It broke down in the launch phase. So if you do that, it's not going to improve students' learning. So we tried to raise this issue with no success. We went away, we redid the case study, and the big change we made was to also provide them with, we had to reconstruct it, but basically the students' work, the information and what they were doing. We came back And we said, here, look at this. And we oriented them. Ask yourselves, would you be able to have a productive whole class discussion if this was the student work? And they decided, no, they couldn't. Why did they all say we have to focus on whole class discussions initially? Because that was the district priority. And if you look in the coaching literature, you will find there's almost nothing about coaches identifying productive improvement goals for teachers. And when goals are mentioned, typically it's either you ask the teacher what he or she wants to work on and go with that, or you go with a district priority, regardless of whether it's productive. And so we found it important to introduce what we call a goal setting process. And I'm not going to go through the details, but basically they don't rush in there and start working with the teacher. They rush in there to learn about the teacher's current practices. Maybe they have a little yes, that appears to be pretty critical and so on. And for us, a productive goal has the following characteristics. It's a feasible next step for this teacher's learning, and it's likely to result in improvements in students' learning immediately if it's attained. And again, remember, for us, improving teaching's at the service of improving learning. And we found, as we worked through this, that two key questions for teachers to ask is, what was the range of students' solutions rich enough to have a productive discussion? Were students able to work meaningfully, all students? If not, there's a problem. Those students who weren't able to work on the task wouldn't benefit for the whole class discussion. The reason why we ask teachers to think about these two questions, it tells them whether the learning broke down before the discussion or not. If it did, then they need to look at the earlier parts of the lesson to figure out in which phase did the learning break down. And that's where they need to target their efforts. If they can support teachers in improving that phase, it's going to result in improved student learning. And I took it out. We actually have a little tool, just sort of a figure thing, to help teachers guide coaches through this process. And then as part of this, I just want to give you one more example of what we think is the level of detail we have to drill down to. So we talked about debriefing conversations. What does the productive debrief conversation looks like? And here's where we've ended up. When you look at most coaches, even pretty good coaches, when they're working with teachers, what do they talk about with teachers first? Instruction, right? And that's reasonable. Their job is to help teachers in getting better. But what happened about teaching being at the service of learning? We suggest instead you start with the learning. What did you hope these kids learned today? What did you want them to learn? What were the goals? Let's revisit those. What did students actually learn today? So you maybe look at students' work. A good coach would actually go through the student work, so maybe pull out 3 or 4 examples of students' work to share with the teacher and discuss during the debrief. Only then do you turn to instruction. Not, oh, did it line up with what some authority said you should do, but what was the impact of your instruction on the kids' learning today? In other words, you're analyzing instruction in order to explain why the students learned what they actually did learn, which might well differ from what you hoped for. Why was that? And in doing that, teachers and a coach typically identify strengths, but also weaknesses. Those weaknesses, if addressed, can then become new learning instructional improvement goals for the teachers. And if the teacher does make those improvements, student learning will improve, right? Because we've identified weaknesses that are impeding student learning. So let's address those. So this is the sort of thing we do with our coaches. And we find that getting down to this level of detail, we've got actual cases we work through with them, actually makes a difference. The last full year before COVID, we not only videotaped the sessions, we had 8 sessions across the school year, the district standard coach PD, nothing unusual because this was a research project. But we also followed 7 of those coaches as they conducted a coaching cycle between each of the 8 sessions. And we then coded their enactment. So we were able to code each of the 3 phases of the cycle. We also had little interviews with the coaches and also one interview with the teacher. And we coded that lot, and we could see the progress in them improving, in identifying productive goals, and also negotiating those goals with teachers so that teachers came to see them as worthwhile and so on. So we did make some significant progress. And you remember earlier, I mentioned those practical measures. We also integrated the practical measures, the student surveys, into the coaching cycle as an additional, not the only, heavens no, student work is still absolutely critical, but also those surveys into the coaching cycle. The coach would administer them a survey that lines up with the instructional improvement goal at the end of the classroom phase. And then they would also analyze that in the debrief phase, asking things like, why was it most of the students responded this way, and relating that to the teacher's instruction as well as the student work. So that's everything I've got. Greg was nice enough to mention this book. This is just pulling together all of our findings from that project that went through 2016. We had a lot of findings, and it's sort of going all the way from the classroom to the district central office. But here are 2 websites. The first one, you can download a whole bunch of stuff from that big project. And the current work on practical measures, you can actually download the measures. They're open access from this website. So thank you very much for your patience.